What's up guys, it's me Sir Ernest, and today we're going to talk about velocity and acceleration in Cartesian coordinate system. So let's recall first the concept of position in Cartesian coordinate system as well as displacement. So if this is your x, y, and z coordinate system or Cartesian coordinate system, we can define the position of the particle at this point to be r. So this is r as a function of time. Now at time delta t plus t, so that means at a certain after some time interval, the particle, let's say, move from this point to this point. Okay, so this is position 1. And at a later time, this is position 2. So the new position vector will now be given by r vector at time equals t plus delta t. So from here, we can define the displacement vector delta r, where delta r, or the displacement vector, is given by the final position r at time equal to t plus delta t minus r at time equal to t. So this is your final position and this is your initial position. Now this displacement happened at time interval delta t. So from here we can define, first we can define the average acceleration, average velocity, sorry. So we usually write average velocity to be v bar or just v average. So by definition, for this time interval between point 1 and point 2, the average velocity will just be the displacement divided by the time interval. So this tells you the rate at which the position change with after a period delta t. Now, if we let, for example, choose a time interval that is very small, so let's say at this position, so this will now be your infinitesimal displacement dr, and this happened at dt. So this dt is a small variation in time, okay, from the initial position r. So from here we can actually now define the instantaneous velocity, or simply velocity. Okay, so from the definition of average velocity, the instantaneous velocity v vector will just be the displacement at the rate at which the position changes with time, but we let dt delta t to approach 0. So you already know from your calculus that this quantity is actually the derivative of the position at this point, okay, at very small interval dt. So if we're going to graph the position versus time graph, so let's say the position changes like this. The velocity, let's say at time t, will just be the slope of the graph. So the slope of this line at this point. Okay. Now, in unit vector notation, the velocity will now be equal to the derivative of r with respect to time, and we already know that r is equal to x I hat plus y j hat plus z k hat. So if we're going to differentiate this with respect to time, this will now become derivative of x with respect to time I hat plus derivative of y with respect to time j hat plus derivative of z with respect to time k hat. And here we're going to introduce what we call the dot notation, wherein the dot notation just tells us that what we're doing is a time derivative. So from here, we can actually rewrite v, or the velocity, as r dot, which is equal to x dot I hat plus y dot j hat plus z dot k hat. So when we see a dot above a certain parameter, so that means we're taking the time derivative. Okay, now similarly, we can calculate the acceleration. Okay, so from these two definitions, we can actually express a similar expression for acceleration. So the average acceleration, a bar, or just a average, will just be equal to the change in velocity at the same given time interval delta t. From here, we can define or write the instantaneous acceleration a vector, which is just the limit of the average acceleration as delta t approaches 0. Okay, so by calculus, this is just the derivative of the velocity with respect to time. Or using your dot notation, this is just simply v dot. In terms of the position, we can actually do this twice. So we're now doing this. We're now going to write the acceleration as r double dot. Okay. So in unit vector notation, similarly, we can express acceleration to be the second derivative with respect to x I hat plus second derivative of y with respect to time j hat plus the second derivative of z with respect to time k hat. And finally, in dot notation, we can actually write this as x double dot I hat plus y double dot j hat plus z double dot k hat. Taking note that r double dot is the second derivative of position with respect to time. Okay, so that's it. A very quick overview of how we express the velocity and acceleration of particles in Cartesian coordinate system. Okay, so that's it. And in the coming videos, we're going to apply these concepts in actual systems. But for now, thank you guys for watching, and I'll see you guys in the next video. Bye-bye.